Welcome back to Introduction to Higher Mathematics. In our last lecture, we saw just where the real numbers came from. We started by constructing the natural numbers out of Peano's axioms. We then constructed the integers and rationals as ordered pairs, each with its own equivalence relation. The ordered pair AB represented the integer A minus B, and then the rational number A over B. We tried to construct the real numbers by extending Q to include the roots of various polynomials with integer coefficients. But alas, this set was only the real algebraic numbers, which is a countable set. All the transcendental numbers were left out. So instead, we took a different approach, constructing the real numbers from Dedekind cuts, which split the rationals into two distinct sets. The irrational numbers turned out to be wholes in the rational numbers. We defined operations on real numbers by working directly with the Dedekind cuts. Finally, we saw how our construction of the real numbers leads us to an important property, the supremum property, which states that, unlike the rationals, if a set of real numbers has a supremum, then that supremum must itself also be a real number. With the real numbers fully constructed, we can soon dedicate some more time to investigating how they work. To begin with, we need to define a notion of size or distance for the real numbers, what mathematicians call a metric. The most common metric for the real numbers is the Euclidean metric, though you probably already know it as the absolute value. It helps if you don't think of the absolute value as making the number positive, but instead measuring the size of a number. More importantly, if we have two real numbers, a and b, then the absolute value of a minus b is effectively the distance between the two numbers on the real number line. The Euclidean metric isn't the only kind of metric, though, so let's take a look at the general properties of a metric. Formally, a metric is a distance function, d, that takes in two objects and outputs a distance between them, which is generally a real number. In addition, to qualify as a metric, our function must have three properties. First of all, it must be what's called positive definite. What this means is that a distance must be greater than or equal to 0. It wouldn't make any sense if a distance could be negative, would it? And also, the only way for the distance between the 2 points to be 0 is if the 2 points are actually the same point after all. Second of all, a metric must be symmetric. This has a similar meaning to when we use the word with respect to relations. Basically, the distance between A and B should be the same as the distance between B and A. Finally, a metric must satisfy what is known as the triangle inequality. The distance between 2 points A and B must be less than or equal to the sum of the distance between A and some other point C and the distance between that C and B. In essence, the triangle inequality is the mathematical way of saying that the shortest distance between 2 points is a straight line. You can't make your distance any shorter by stopping by an intermediate point along the way. Anyway, if these three conditions are met, then our function d qualifies as a metric. When we take a set like the real numbers and equip it with a metric, we have what's called a metric space. Basically, a set with a way to measure distances between elements. Now, the reason we call the absolute value the Euclidean metric is that it extends quite well to higher dimensions of Euclidean space. Think for a moment about how you would measure the distance between 2 points in the plane. You just use the distance formula you learned in basic algebra. The distance between 2 points is the positive square root of the difference in the x's squared plus the difference in the y's squared. That formula is actually the definition of the Euclidean metric for r squared, which, as we mentioned earlier, is the set of all ordered pairs, representing a two-dimensional plane. You also might have learned the distance formula in 3D. We just add a difference in z squared under the square root. This, unsurprisingly, is the Euclidean metric for r cubed. But then how does that translate to an absolute value in just R? Well, we might modify our distance formula for just single real numbers so that it's just the positive square root of the square of the difference between two real numbers. So there's a square root of a square. Well, wouldn't those just cancel out? Not really. Remember that we said the positive square root, since every real number, remember, has two square roots. So our answer, which must be positive, will effectively be the absolute value of the difference between the two numbers, since the absolute value also is always positive or zero. With the notion of a metric now in our arsenal, we're going to start to explore what's known as the topology of the real numbers. Topology comes from the Greek topos and logos, meaning place and study. It's basically the study of the most basic properties of space. As a field of mathematics, topology is somewhat more recent than many of the topics that we've been covering, having had most of its developments in the latter half of the 20th century. We'll be talking mostly about topological concepts involving sets, which is a bit different from the topology involving geometrical objects that you may have heard of, although the two kinds of topology are related. Although we're mostly interested in how these concepts apply to the real number line, we'll often be visualizing them first as if they're in R squared as well, because some of the concepts are a bit easier to see in R squared. We'll also often be referring to the elements of these sets as points on the real line, on the plane, in space, or whatever's relevant at the time. Also, in each of these, we can assume that we're using the usual Euclidean metric to measure how close things are to each other. Technically, it's possible, and quite common, to do topology entirely without using a metric, instead entirely using the concepts we're about to define. But for the purposes of this lecture, we'll take advantage of the Euclidean metric as our pretty easy to use measure of closeness. So the first thing we need to do is define the concept of a neighborhood. A neighborhood of a point is the set of all points that are within some specified distance from that first point. The points in the neighborhood should be less than that distance away, never equal to. In math, we often use the lowercase Greek letter epsilon to denote a small distance, in which case an epsilon neighborhood of a point is a neighborhood where all the points in the neighborhood are within a distance of epsilon from that first point. That epsilon is generally called the radius of the neighborhood, as you can see why from the diagram. We often are concerned with epsilon neighborhoods in math because we're concerned with what happens when we make very small changes to numbers, especially when we study calculus. So in the real numbers, what would a neighborhood look like? Suppose we let x equal 3 and epsilon equal 0.1. Then the epsilon neighborhood of x will include all the real numbers that are strictly between 2.9 and 3.1. Now, in the real line, this is what we call an interval. An interval is a set of all numbers between two endpoints. In particular, we call this one an open interval, which we notate with parentheses. Note that this is not to be confused with an ordered pair in the plane. But really, that shouldn't be much of a problem, since you should pretty much always be able to tell whether we mean an ordered pair or an open interval by just looking at context. Now we can generalize this idea of an open interval and introduce the notion of an open set. An open set is a set such that for any element of the set, we can find an epsilon greater than 0, such that the epsilon neighborhood around that point is contained completely within the set. If that seems a bit complicated, think of it this way. If a set is open, then from any point inside the set, we can move a little bit in any direction and still be in the set. So the open interval from 2.9 to 3.1 is a great example. Say you pick a point in this interval, perhaps 2.95. Then I can find a small enough neighborhood around 2.95 if I let epsilon be 0.025. Then the epsilon neighborhood of 2.95 is the open interval from 2.925 to 2.975. On the other hand, What if we consider the interval from 2.9 to 3.1, but we include 2.9? Will this set be open as well? Well, look at the point 2.9. No matter how small we try to make epsilon, any neighborhood we try to find around 2.9 will have to contain numbers that are less than 2.9, since we said epsilon can't be 0. So this interval is in fact not open. By the way, as a quick side note, at times we have to be a bit more specific when we talk about a set being open, and say that it's open in some other set. For instance, even though our interval from 2.9 to 3.1 exclusive was open when we were only considering the real line, it would no longer be open if we were considering it as a line segment on the x-axis in the xy plane. We could move up or down and no longer be in our line segment. So we would have to say that the interval from 2.9 to 3.1 exclusive is open in the reals. In most cases, though, and throughout this lecture, you can assume that this suffix of in the reals is implied. So how can we combine open sets? We can take the union of any number of open sets, and we'll still have an open set. With intersections, though, it's a little tricky. We have to be careful. The intersection of a finite number of open sets is open, but the intersection of an infinite number of open sets might in fact not be open at all. For instance, consider the following open intervals. Let's look at the intersection of the intervals from -1/2 to 1/2, -1/3 to 1/3, -1/4 to 1/4, and so on, shrinking our interval down each time. If we keep doing this ad infinitum, the only point that will be left in our infinite intersection will be a singleton set containing just the number 0. And the set containing just 0 isn't open. Any non-zero epsilon neighborhood I can make around 0, no matter how small, must contain real numbers that are not equal to 0. Now let's make another slight modification to our interval. Let's look at the interval from 2.9 to 3.1, but this time include both endpoints. This is another kind of interval you've probably heard of before. We usually call this a closed interval. And rather than using the curvy parentheses as we did for open intervals, we usually notate closed intervals using square brackets. As you may imagine, our next step is therefore to generalize this idea and define the notion of a closed set. Now in English, the words open and closed are opposites, so you may be tempted to think that a closed set is just one that isn't open. However, this is not the case. Be careful not to make this simple but major mistake. It's at least close, though, but we have to be a bit more precise. In particular, we say that a set is closed if its complement is open. So take a look at our closed interval from 2.9 to 3.1. Now it's including both endpoints. What would the complement of that interval be? Well, let's break it down. What we mean when we say that x is between 2.9 and 3.1 inclusive is that x is greater than or equal to 2.9 and x is less than or equal to 3.1. So by De Morgan's laws, remember those? The complement of this interval should be the set of all x such that x is less than 2.9 or x is greater than 3.1. That's a union of two open sets, so it's guaranteed to be open as well. So since the complement of the interval from 2.9 to 3.1 inclusive is open, we verified that that interval itself is in fact closed. De Morgan's laws again come in handy when looking at the unions and intersections of closed sets. Now suppose something is not in the union of a bunch of open sets. Then it must be in the complement of that union, which by De Morgan's laws must be the intersection of those complements. But since that union can itself be thought of as one big open set, its complement can be thought of as one big closed set. So in the case of closed sets, we can take the intersection of any number of closed sets and we'll still have a closed set, It's basically the opposite of the rule for open sets. On the other hand, we can only take a finite number of unions of closed sets and still be guaranteed a closed set. If we take an infinite number of unions, we might end up with a set that isn't closed. For instance, consider the union of the closed sets from -1/2 to 1/2, -2/3 to 2/3, -3/4 to 3/4, -4/5 to 4/5, and so on, this time expanding our interval each time. If we keep going in this fashion unto infinity, the union of all of these sets will be the interval from -1 to 1, exclusive. The bounds of all of the intervals I've been mentioning get closer and closer and closer to the numbers -1 and 1, but they never actually get there, so it's an open interval. The complement of this set is the union of the intervals from -infinity to -1, including -1, and from 1 to infinity, including 1. As I of course invite you to verify, the set formed by these two intervals is not open. So the interval from -1 to 1 exclusive is therefore not closed. Now remember how we just said that just because a set is not open, that doesn't mean it's closed. By the same token, just because a set isn't closed, that doesn't necessarily mean that it's open. We can have sets that are neither open nor closed. For example, consider the interval from 2.9 to 3.1, including 2.9, but not including 3.1. The set isn't open because if we try to create a neighborhood around 2.9, we'll always include points that are not contained within the set, that are less than 2.9. But the set isn't closed either, because if we take the complement of it and then try to create a neighborhood around 3.1 instead, that will contain points that aren't in the complement, points that are less than 3.1. So the interval we've just described is neither open nor closed. Now in the real numbers, we often notate this particular kind of interval, which is sometimes called a half-open interval, by combining the symbols from our open intervals and our closed intervals. A square bracket on 2.9 because it's included in the interval, and a curved parenthesis on 3.1 because it isn't included. What's more, and this is even stranger, we can actually have a set that's both open and closed. As mind-boggling as it sounds, if we follow our definitions carefully, then we'll find that it's true. Suppose the universal set is the real numbers. Consider the entire real line. If we pick any real number, then any neighborhood we draw around it will contain nothing but real numbers. So the entire set of real numbers is open, in the reals at least. Now consider the complement of the real line. Since the universal set is R, the complement is the null set. Is the null set open? That would basically be saying that for every point in the null set, we can find an epsilon neighborhood around it that is completely contained in that null set. But wait, there is nothing in the null set. This is just like what happened back in our first lecture on set theory, when we said that the null set is a subset of any set. Our condition has been shown to be vacuously true. So the null set is open as well. But look, since the real line and the null set are complements of each other, basically think of them as everything and nothing, that implies that both sets are closed as well. So the real line and the null set are both open and closed. Now, topologists have a name for these sets. They call them clopen. Yes, clopen. I'm not kidding. You can groan and roll your eyes now at the terrible name, but I'm afraid that's just how it is. But at least we don't have to deal with these sets too often, though, right now. It can be proven that the entire real line and the null set are the only clopen sets in R. And of course, I'm sure you're eager to go off now and try to prove that yourself. So now that we've seen what open and closed sets are, let's talk a little bit more about the contents of these sets. Generally, a set S can be broken into three parts: its interior, its exterior, and its boundary. Let's see what these are. A point is an interior point of S, if we can find a non-zero epsilon neighborhood around it that's contained completely inside the set. Then the interior of the set, which we would write as int of S, is just the set of all such interior points. We can also think of the interior of S as the union of all possible open sets contained within S. Or, since a union of open sets is open, we can think of it as the largest open set contained in S. In fact, this gives us another somewhat more concise way to define an open set. A set is open if and only if each of its points is an interior point. This is something we do rather often in math. We define some concepts, define some more concepts, and realize that those new concepts can be used to better define the old concepts. These relationships are essential to understanding what's going on, so try to make those connections whenever you can when you're studying math. Let's continue. A point is an exterior point of S if we can find a non-zero epsilon neighborhood around it that's completely outside the set. Or, as we might more precisely say, it's contained completely within the complement of the set. Then the exterior of the set, which we would write as ext of S, is just the set of all such exterior points. In fact, we can think of the exterior of S as the interior of the complement of S. As before, we can also say that the exterior of a set is the union of all possible open sets that are completely disjoint with S, or the largest open set that is disjoint with S. Finally, let's talk about the boundary. A point is a boundary point of S if any non-zero epsilon neighborhood around it, no matter how small, must contain both points inside the set and points outside the set. In other words, it must contain both interior points and exterior points. Then the boundary of the set, which we would write as BD of S, is just the set of all boundary points. The boundary gives us yet another way to easily characterize open sets as well as closed sets. We can say that a set is open if and only if it contains none of its boundary points. On the other hand, a set is closed if and only if it contains all of its boundary points. If a set contains some of its boundary points, but doesn't contain others, then it's neither open nor closed. And in addition, if a set has no boundary points, like, say, the real line in the null set, then the set is clopen. These definitions of open, closed, clopen, etc., using boundary points, are a little bit easier to use than some of the ones we used previously, but we had to kind of build up to them. To solidify our understanding of these three concepts, let's consider the real interval from earlier, from 2.9 to 3.1, including 2.9, not including 3.1. We're going to be using this interval quite a bit, as you can tell. The interior of this set would be the open interval from 2.9 to 3.1. Any real number that's strictly between these two numbers will be an interior point of the set. For example, if we were to consider, say, 2.91, the open interval from 2.905 to 2.915 would be contained completely within our interval. The exterior of the set would be a union of two open intervals, one of them from negative infinity to 2.9, and one of them from 3.1 to positive infinity. Any number in one of those two sets has a neighborhood around it that is completely outside the main interval. For instance, consider 3.11. The interval from 3.105 to 3.115 is still contained in the complement of the interval. Finally, the boundary of this set comprises two individual points, 2.9 and 3.1 themselves. We can see that our interval contains one of the boundary points, 2.9, so it can't be open. But it doesn't contain all of the boundary points, 3.1 is left out, so it also can't be closed. So we can see that our interval is neither open nor closed just by looking at the boundary. By the way, sometimes a set S isn't closed, But since closed sets are often useful for various things, we may want to sort of close it off. So, we might want to add the minimum number of points that will ensure that our set is closed. What we then have is called the closure of S, written as S bar. That's the smallest closed set that contains our original set. So, what is the closure of a set? Easy. It's just the interior of the set union the boundary of that set. If we include our entire boundary, then as we saw earlier, the set is closed. So for example, the closure of our interval we were just looking at will be the closed interval from 2.9 to 3.1, including both points of the boundary. Okay, so let's look a bit more at these sets and talk about connectedness. A set can be connected or it can be disconnected. I'm sure you can visualize intuitively what these concepts might mean, but as is the way of mathematics, we need to define them formally so we can use these definitions to our advantage. We're actually going to start off with what it means for a set to be disconnected. We say that a set S is disconnected if we can find two open sets U and V that satisfy three particular conditions. First of all, U and V must both intersect the set S, meaning U intersect S and V intersect S should both not be empty. Second of all, U intersect S and V intersect S should have nothing in common. In other words, their intersection should be the null set. Finally, the union of U intersect S and V intersect S should be the entirety of S. If all three of these conditions are met, then the set is disconnected. Basically, what this means is that a disconnected set is one that can be enclosed by two non-empty open sets, splitting the entire set into two pieces that have nothing in common. By the way, if S itself is an open set, then it becomes even easier to show if it's disconnected. All we need to do is find two open sets U and V such that U intersect V is empty and U union V is the entire set S. Now, with the definition of a disconnected set out of the way, the definition of a connected set is pretty easy. A set is connected if it's, well, not disconnected. Simple as that. So for example, our interval from 2.9 to 3.1 is connected. Basically, it's all in one piece. Proving this is somewhat harder than it looks, though. Even though it seems obvious, you'd basically have to do it by contradiction. On the other hand, what if we took out 3? Is the interval still connected? Well, now we could enclose the two halves of the interval in open sets. Perhaps we could let U be the open interval from 2.8 to 3, and V be the open interval from 3 to 3.2. Then the intersections of these two sets with S, which are non-empty, have nothing in common, but together they make up all of S. Thus, by taking out 3, we've made our interval disconnected. What's more, some sets can be what's called totally disconnected. A set S is considered to be totally disconnected if for each distinct X and Y in the set, there are two disjoint open sets U and V, just like earlier, such that X is in U, Y is in V, and the intersection of U and S union the intersection of V and S is the entire set S. What that means is that given any two distinct points, we can always find a way that they're separated from each other. A good example of a totally disconnected set is the integers. Given any two distinct integers, we can always make two open sets, one called U that goes from negative infinity to the lower of the two numbers plus 1/2, and one called V that goes again from that lower number plus 1/2 all the way to positive infinity. These two sets, U and V, are disjoint, but each one is guaranteed to have exactly one of the two integers. What's more, the way we've set it up, the intersections of U and V with the integers, when unioned together, end up being the entire set of integers. So we can conclude that the integers are totally disconnected. There's one more concept in point set topology that I'd like to go over, the idea of cluster points. A cluster point of a set S is a point which may or may not actually be in S itself, such that any non-zero epsilon neighborhood surrounding it, no matter how small, contains at least one other point of S. That is, other than the cluster point itself. The idea is no matter how close you zoom in to look at a cluster point, there will always be other points that are close to it in a sense. In fact, this implies something rather interesting. If there's at least one other point in the neighborhood of a cluster point, then there's actually an infinite number of other points in that neighborhood. Why? Well, suppose that weren't the case, and instead there were a finite number of points around our cluster point. We can measure the distance from each of these points to our cluster point. Because the set of points is finite, we can of course find the closest one, the point for which the distance is the minimum out of all the other distances. This is guaranteed because a totally ordered finite set always has a maximum and a minimum. But wait, then we could just create an epsilon neighborhood around our cluster point where epsilon is half of that minimum distance. Now we've got a non-zero epsilon neighborhood with no other points in it, which contradicts our definition that said that was a cluster point. So we can conclude that if there's one other point in any epsilon neighborhood of a cluster point, then there must in fact be an infinite number of points in any epsilon neighborhood. This actually helps the word cluster make a little more sense here. The idea is that the other points cluster around the point, and we can get closer and closer to the point while still being in the set, without actually touching that point. Note again, however, that a set does not necessarily have to contain its cluster points. The boundary points of the open interval from 2.9 to 3.1 are both cluster points, but obviously they're not in the set, because they're the boundary points of an open set. Another thing to watch out for is that not all boundary points are cluster points. Look again at the set of integers. The integers are a closed set in the reals, which you can verify. Think about what the complement of the integers in the real line would be. But the set of integers has no interior. It's nothing but a boundary, basically. But for any integer, we can easily create an epsilon neighborhood around it that contains no other integers. Simply let epsilon be less than or equal to 1. This leads us to another definition. If we can find a non-zero epsilon neighborhood around a point x of a set S, such that the neighborhood contains no other point other than x itself, then we say that x is an isolated point of S. Basically, if we zoom in close enough to an isolated point, it'll be completely by itself. Now, before I close out this lecture, I'd like to introduce you to a truly bizarre set that has some strange properties, called the Cantor Set. Here's how Cantor came up with this set. First, we start off with the closed real interval from 0 to 1. Next, we delete the middle third of the set, the open interval from 1/3 to 2/3. So now we're left with two closed intervals, one from 0 to 1/3 and one from 2/3 to 1. Now, we do it again removing the middle third of each interval that's left over. Now we're leaving four closed intervals, 0 to 1/9, 2/9 to 1/3, 2/3 to 7/9, and 8/9 to 1. Then we do it again, and again, until infinity. What we're left with is Cantor's set, a very delicate sort of set, almost like dust, if you will. So let's look at some of the properties of the Cantor set. First of all, as ghostly as this set seems to be, it is actually not only infinite, but uncountably infinite. There's a good reason for this. You may already be familiar with numbers in binary, which are represented with only zeros and ones, for which each place value represents a power of 2. Well, we can also write numbers in ternary, in which each power instead represents a power of 3, and the only digits we use are 0, 1, and 2. Basically, for a number to be in the Cantor set, it must be able to be represented as a ternary number starting with the 0 point, and from that point on, containing nothing but zeros and twos, no ones allowed. Then from there, we can just apply Cantor's diagonal argument from a couple of lectures ago, swapping the zeros and twos to get a new number, and that shows that the Cantor set is uncountable. But it gets stranger. Every point in the Cantor set is a cluster point. Any neighborhood of a point will contain other points, in fact, infinitely many other points that are also in the Cantor set. But that same neighborhood will also be guaranteed to contain points that are not in the set. So the Cantor set has no interior. In fact, the Cantor set is totally disconnected. A property we might expect of a countable set such as the integers, but certainly not something we'd expect of a set with uncountably many points. I could go into an entire lecture on just the oddities of the Cantor set, but that would be going a bit too far off topic. And besides, it would ruin the fun of you going and looking up the Cantor set on your own. Anyway, that's it for this lecture. In the next lecture, our discussions of cluster points are going to come in particularly handy when we talk about sequences and functions. That's when we'll start to introduce limits, which are usually the beginnings of calculus. See you next time.